Okay, this time I'm not going to show more slides. So this was yesterday slide. You can look at this, especially the formula. Although I hope, I believe that you have absorbed this formula of the angle between. I guess I should use also not between, but the angle from U to V in general, because when V has that dimension larger than U, then you cannot reverse. Okay, but if the dimensions are the same, then you can reverse. Okay, I wrote the title of the paper that I will relate to the computation that I will do today. Will be related to the formula in this paper by Norman Wildberger. Published in 2017. So the title of the paper is Rational Trigonometry in Higher Dimensions and a diagonal rule. So not all of the stuff in this paper is relevant, of course, but I should write the titles completely. So for dimensional space. So this is published in the journal abbreviated as COG. So I think it's a Croatian journal. I don't know what it stands for, maybe Croatian geometry or something. You can check the internet. The volume, I think, is 21. Okay, so in this paper, Waldberger obtained a formula for the square. So it's a formula. For the square of the cosine of the angle between, you use the word between because the subspaces are out of same dimension of two subspaces U and V of dimension P in Rn, in the Euclidean space. And the formula is given by this cosine squared theta equals the determinant of now PRT RRT inverse RP transpose, and then PP transpose inverse. It's a weak formula, so I call this star. So here P is a matrix whose first row is the vector U1. So I just write sign U1 here. So it will be U11, U12 up to U1n, and up to UP. And these UIs are the basis of U. And R is similar, so R consists of the vectors Vi up to Vp, which are basis of V. Okay. So since U and V are of the same dimension, so this is P by P, right? Sorry. This is not a square matrix, so it's P by N. This is also P by N. But when you take the transpose, this is N by P, so that product is P by P, P by P, and so on. Okay? So clearly, since P R transpose R transpose, and so it's inverse R P transpose and P transpose are all square matrices, then you can use the property of determinant. Determinant of A times B is determinant of A times determinant B, and the determinant of the transpose is the same as the determinant of the matrix, and the determinant of the inverse is 1 over the determinant. So you can see clearly that we have here that the cosine square theta is equal to the determinant of P times R transpose times the determinant of R P transpose. Basically, this is A, B, C, D. So determinant of A times determinant of B times determinant of C times determinant of D. But determinant of D is 1 over the determinant of R transpose. So I put that at the bottom. Times the determinant of B transpose. So this is exactly, and this R B transpose is the same as the determinant of R B transpose is the same as the determinant of P R transpose, because that matrix is the transpose of that. Okay, so clearly we have this formula. And this is exactly what we had yesterday when U and V are of the same dimension. So that one, okay? That is exactly the same. But now, question raised. What if, so the question is, what if R consists of more factors than P? So up to VQ, say, with Q larger than P. So what happens? So that was the question that Wahlberger asked me. You have a formula, right? I said, yes. I have this formula, and I believe that my formula also works for Q greater than P. But what I want to know is, whether my formula is identical with yours. That's what he said. I visited him in December last year only for 5 days, so I tried to work out in the last maybe 2 days, so but I didn't spend maybe the whole 2 days. First, I checked in the case where P is equal to 1 and Q is greater than 1, so I go back to this formula. Remember that from this formula I could get that, and also when Q is greater than P, I have this for P equals 1 and Q equals 2. Okay, so maybe I will check this first. Okay, for you also it's good to know how things go in the simplest case. So let's see the simplest case here. P is equal to 1, Q is equal to 2. Okay, so P is just a 1 by 1 matrix. Sorry, 1 by n. Still, we are still in Rn. Okay. So I should write. This is U in this means U1 up to Un. This is 1 by n. And Q and R is V1 and V2. Okay. So this is 2 by this. Note that R transpose is V1, 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 V2, V2, V1, V2, V2. This is the grand matrix consisting of V1 and V2, and so its inverse is given by this. You know the inverse of a 2 by 2 matrix, right? So the determinant should be, this is the determinant of this, the square of the 2 norms, and this is V2, V2 minus, now you can say it's V2 minus, I put the minus inside, and write it in front of V1 for some reason. So I write it minus V1 minus V1. Of course, it is the same as. So it's just like replacing V1 by minus V1 and then change the position. So now I check. Maybe I write again the formula while burger is then cosine squared theta is the determinant of one formula P R P R P inverse and then R inverse. Okay, so actually I continue a little bit here. From this formula we can say that I can break up these two guys because they are square matrices of the same guy. But I cannot break this tree because these are not square anymore now. Okay? This is about P by Q, Q by Q, and I cannot take the one in the middle because matrix multiplications is not commutative. Okay, so that's why this is a bit tricky. But that one I can separate. Okay, so this is the Weilberger formula. Don't ask me where he got the formula. He uses a lot of simulation with his computer and maybe his algebra knowledge. Okay, so we come back to this. So I first compute. I have computed RR transpose, and now if we check PR transpose times RR transpose inverse times RP transpose. So this will become 1 over. This is just a scalar. I can write that first, and then I have the PR transpose. Maybe this is not the most efficient way, RP transpose, but this was what I did last time. So with the R star here is V2 and minus V1. Okay, so that's why I took the minus attached to V1, so I can write, so I have R star here, V2 and minus V1. So this is just 1 by 2, this is 2 by 2, and this one is 2 by 1. So this is actually 1 by 1 matrix. So it is actually a number at the end. But now, let's see what this is. So this is UV1, UV2. That is P times R transpose. And then in the middle, I have the one from the inverse of R transpose. So I have here V2, V2, V2 minus V1, minus V1, V2, and then minus V1, minus V1. And then I have UV1 and UV2. Okay? And you work this out, you can do the multiplication. Okay, that's a little exercise. At the end, you'll get, from this multiplication, you get the two inner product of V1 with V2, and then the other one, you get V2 with V1, and you divide the whole thing by V1, V2 squared. And that is exactly what I got here. That one, of course, we haven't divided by this. Okay, we just compute the numerator. So when we divide by the determinant of the transpose, which is the square of the norm of U, then we get exactly the same. Okay, so we get exactly the same. So this is hopeful. So after Norman, his first name is Norman, asked me, I checked with this simplest case first, and then I said, oh yes, it's hopeful. So give me more time to do the general case. Okay, so I then work with the general case. Of course, I have to tell you the truth that at first I get lost, and then I change the strategy, and then the aha moment is something to do with this. So I didn't explain in detail yesterday, but now we should look at this closely, and I will show you how it appears in the computation. So in general, we move, we proceed from the formula, the original formula that I had, which is this. So now P is anything, Q is, so that's the case, right? So P can be 1, Q can be equal to P, but we have done that already. But in general, of course, we can put all the possibilities there, so that's the general case. So U1 projected to V, up to UP projected to V squared divided by the n norm of U1 up to UP squared, the original volume. So the volume of the projected parallel pipe squared divided by the volume of the parallel pipe, the original parallel pipe squared. So here UI V is the short for the projection of UI on V. So I goes from 1 to P. So now let UIV is like I wrote there, linear combination of Vk. K goes from 1 to Q. By the way, I should tell you also why Ristesky and Terzowski formula didn't work out, because remember when we try to reduce from any basis to orthonormal basis, we always have cancellation on the numerator and denominator because of the same size. Because when I divide by the norm of UI here, then also the norm of UI there, same size. But when we divide by the norm of VI, on top we have P times Q and Q times V, something like that, and on the denominator Q by Q. So they don't cancel actually. So we cannot go from orthogonal to orthonormal. So that's why my counterexample orthogonal, but formula didn't work. The formula only worked for orthonormal basis for V. But the step that they missed was in the very first sentence. Without loss of generality, assume that. So you have to really be sure when you say without loss of generality, assume that something. Okay. So sometimes we think too lightly about something which is actually very important. Okay, so now let this is the linear combination. Let this be the linear combination of Vk. So draw this picture just for illustration. So if that's our UI, and this is the projection UI V, then this orthogonal vector is UI minus UIV. And this UI minus UIV is orthogonal to V. So I have here that VL, the basis of V, the inner product with the UIV is 0 for each L from 1 to Q. So I have a system of Q many linear equations here. I can break this up. So I have this is equal to VL UI, and this is for L from 1 to Q. Okay. So now I substitute what UIV is. So I have 1 alpha IK VL VK. K goes from 1 to Q. This is a VL UI. This is still for L from 1 to Q. Then this is equivalent to the following equations. VQ V1, VQ VQ, and this is alpha I1 up to alpha IQ. V1 UI, VQ UI. Now, of course, this is just a linear algebra. The determinant is non-negative, so it has a unique solution, and the solution is given by this. This is just the inverse. The inverse axis, VI UI up to Q UI. What is this matrix? This matrix is nothing but R transpose. Okay? My joint paper, I use Cramer's rule for the solution of this. I use Cramer's rule. That's why I get this n inner product over that. Basically, if you do that, then you come to this formula, right? But now, don't do that. This is exactly R transpose inverse times R transpose. So, using Wahlberger's notation, that's that. And sorry, I should have an index here, I. This means the I column of R transpose. Okay? Because there is I there. So you do this for I equals 1, you do also this for I equals 2, and so on. So each time you get the I column of. So that means if you do it simultaneously for all i's, then you get exactly R transpose inverse times R B transpose. So now instead of using the Cramer's rule to find the alpha j k's, we use the inverse of RR transpose, and note also that one more step is of course to compute this thing here. So for that, we have to compute this, because this consists. This is a gram matrix whose entries are the inner product of UIV and UJV. Okay, so I want to compute that, and again, by adding nothing to get something, the first vector can be replaced by UI. Okay, why is that? Because I add the orthogonal projection. Okay, I add the orthogonal projection. The orthogonal projection inner product with something there is 0, so I do that, and this is alpha jk ui vk, which I just wrote there, and I just computed the scalars. So here I and j goes from 1 to p. Hence, the anon square of UIV up to UVV is the determinant of these guys, alpha 1k u1 vk, k goes from 1 to q, and then the last term in the first row will be alpha p k up vk, and the last term in the first column will be alpha 1 k up vk. Sorry, this one is u1. What changes here are only the scalars, right? Okay. And then the last entry here is alpha pk up vk. Okay, I have already. Okay, so this is nothing but the determinant of this matrix u1 v1 up to u1 vq, up v1 up to vq. Sorry, of course this is not a square matrix, it's p by q, but I haven't finished writing. So this is our alpha 1 1 up to alpha 1 q. So this will be q by p. Okay, there are q manis here. So this times that and so on. That is the first entry, and alpha p1 alpha pq. So q rows, p columns, but each column is is a column from R times P transpose. So that is, and this, the first is P R transpose, so we recognize this as P R transpose. And what is this? We say, okay, the determinant is the determinant of these two matrices. Okay, so the first matrix is that guy, and this matrix, yeah. So the ith column of that matrix is given by this. Okay, so so the second matrix is exactly this guy. This guy today. Okay. I'm done. So therefore, I have demonstrated that the cosine square theta that I have, that I still have now, is the same as the cosine square theta that Wahlberger has. That is BB square and this is the determinant of PR transpose R transpose equals R P transpose determinant of P transpose, which is exactly what we want to have. So I said I should write this. Yeah, so the only difference is that we sort of branch out from the way we solve or we get the coefficients here. So before I use grammar school, but apparently I don't know if it is what really happens with Wahlberger's in Wahlberger's head. Apparently he used the inverse instead for the solution of these equations. Okay, so the two are identical, as you see, and maybe one has an advantage than has more advantage than another. I don't know which one is really better at the moment, but think about numerical computations. Which one is better in the sense less order of computation? Is it computing the inverse or computing the determinant? I think people in numerical analysis know which one is better. But mathematically they are the same, but computationally maybe they are different. I think I will stop my last lecture there, a little bit shorter than scheduled. Any question? Please. If not, then thank me.